Here is a state diagram that we have seen before, and you now should be able to implement this in Verilog using the canonical form. So we start off with a local param and assign 0 to A, 1 to B, 2 to C, 3 to D, 4 to E, 5 to F, and 6 to G, and then implement this like we did in the previous video. Changing state encoding means that we will no longer call A, represent A by 0, B by 1, C by 2, etc. We can change that. Now if we just swap the numbers around here, well yes, that might make some change, but we're going to do something a bit more radical, and we are going to use what's known as hot encoding. If we have already implemented this in canonical form, then changing to hot encoding is straightforward. We just change the local param statement to be A is equal to, there are 7 states, and so we're going to use 7 bits to store our state, and basically 1 bit is going to represent 1 state. So we can call state A that, state B this, state C this, and hopefully you see the pattern all the way down to state G, which is going to be 1 0 0 0 0 0. This is called hot encoding because only 1 bit is on in the state at any one time. This means that the next state logic doesn't have to waste any effort trying to figure out what state it's in. It just simply has to look at which bit is a 1 and it knows what state we're currently in. This means that if we wanted to, we can actually design this finite state machine by hand. We can design the hardware implementation by hand. Now these days we don't really need to know this because Quartus will just do this for us, but nevertheless, to get some insight into how changing the state representation can significantly change the hardware, we're going to look at this now. Let's start with the output logic to see how easy it is. So we can do assign out is equal to, now out is 1 bit, and out is going to be 0 unless the state is D or the state is G. State D means that the 3rd bit of the state's going to be set, and state G means that the 6th bit of the state is going to be set. Therefore, our output logic is going to be equal to state bit 3 or state bit 6. So if bit 3 of state is a 1 or bit 6 of state is a 1, output's going to be a 1, corresponding to bit 3 represents D and bit 7 represents G. Sorry, bit 6 represents G according to this assignment here that we've made. Sometimes you'll see this written another way by using bitwise operations. We could have had assign out equals state and then we have what's known as a bit mask, and we care about 6-bit, about bit number 6 and bit number 3. So we perform this bitwise and then we test to see if that's not equal to 0. The way this works is that state is a 7-bit number, so bit 6, bit 5, bit 4, bit 3, bit 2, bit 1, bit 0. When we bitwise AND it with this one here, then when we're ANDing it with 0, we're always going to get 0. So we're always going to get 0 there, and we're always going to get 0 here. And for these 2 spots here and here, we will get a 1 if the corresponding bit in state is a 1, otherwise we get a 0. So in other words, if either the 3rd bit or the 6th bit of state is a 1, then this output after doing this AND is going to be non-zero. And so therefore these 2 assignment statements are equivalent. I guess in principle, rather than writing not equals to 0, I could have put out the front here 2 of these signs. So we take not to convert a 7-bit number into a Boolean 0 or 1, and then we take not again because we actually want a non-zero number to be true. And so the first not would have inverted that. We need a second not to get it round the right way again. Yet another trick we could have played is that early on in our module, I mean it can appear anywhere because order doesn't matter, but maybe it's nice to put it early on. We could have written a bunch of statements like wire A equals state 0, wire B equals state 1, and so forth. And if we'd done this, then that means we could have done assign out equals D or G, because D is going to be the same thing as state 3, and G will be the same thing as state 6. Doing something small like this will greatly decrease the chances of making an error in your code by somehow writing the wrong bit in here. That's the output logic done. Let's clear this and look at the next state logic. For our next state logic, we're just going to go bit by bit. So assign next state, bit 0 equals, and we're going to work out a Boolean expression to put here. Then we're going to have another assign next state 1 equals, and another Boolean expression that's going to go here, and we're just going to do this up to next state 6. And once we've done this, we've fully specified our next state logic as well. Remember, we'd probably only do it this way if we were implementing it manually, because there might be easier ways to describe to Quartus what our finite state machine is, and we should take the easiest way of describing it to Quartus, because that will minimize the chance of introducing a bug somewhere in our code. Next state 0 is actually very easy to do. We have a look at state A, because remember bit 0 corresponds to state A. Next state 0 is assigned to a 1 if we end up at state A. But if we have a look here, we never end up back at state A. So this is very easy. Next state 0 is always 0. That one's easy. Let's move on to look at next state 1. So bit number 1 corresponds to state B. So in state B, we're asking ourselves, how can we end up in state B? So it's worth pointing out this thinking is opposite to how we do it in our canonical form. Normally, we've got a case statement that selects, that works out which state we're in, and we say, if I'm in state A, where can I go? But if we're doing this one-hot coding by hand, we're doing the reverse. We're saying, how can I end up in state B? We're not saying, if I'm in state B, where do I go next? We're saying, how do I get to state B? So how do I get to state B? Well, there are lots of ways. I could be in state A and receive a 0, or I could be in state E and receive a 0, or I could be in state F and receive a 0, or I could be in state G and receive a 0. So these are the ways I can get here. Let's have a look at how we can write it. There's a fast way of doing it, but let's do it the slow way first, then I will show you the faster way. The slow way is to go one by one. So how can we end up in B? The first way we said was we are in state A. How do we know that we're in state A? Well, that would be state bit 0 is a 1. So if I'm in state A and if the input is a 0, so not in, then I'm going to move to state B. So therefore this is one term in my expression. But there are other ways I can end up in state B. So I have an OR sign here. Or, what's another way of ending up in state B? I could be in state E. How do I know if I'm in state E? State 4 tells me I'm in state E, and the input needs to be a 0 to get from E to B. So again, not in, or state 5 and not in, or state 6 and not in. And that's the expression for next state 1. We repeat exactly the same procedure for all the bits of next state, and then we're done. Now, provided this is a genuine state diagram, then these logic statements that we write down here, we're guaranteed that for any particular current state and input, only a single bit of next state is going to be a 1. That's because of the properties of this diagram here. And one more time, how does this work? Well, we want next state 1 to be equal to 1 if and only if we move to state B. And so down here, we just list the different ways of moving to state B. This you'll recognize as a sum of products form, by the way. We're basically just selecting the different ways, the different combinations in my truth table, the different rows in the truth table that will give me a 1 for the next state here. So to get a 1 here, because we have ors here, it means either this is a 1, or this is a 1, or this is a 1, or this is a 1. And each one of these is going to be a 1 if we are in this state and the input satisfies this condition. Not in is going to be true whenever in is 0. So this expression here gives us a 1 when the input's 0 and we're in state corresponding to bit number 4 being a 1, which in this case is state E. I mentioned a faster way of doing this, and that's simply observing that we can factor not in out of everything. Because of this particular state diagram, which is detecting either the sequence 0, 0, 0 or the sequence 1, 1, 1, to get to B, the input has to be 0. So we don't have to repeat this not in everywhere. And we would have seen that immediately from this diagram here, and so we could have instead written immediately that we want not in and then we just OR together the different possibilities of the states. So state 0 or state 4 or, and I'm running out of room, state 5 or state 6. And so that would have been an even faster way to write the logic expression for this assigned statement here. The same tricks that we mentioned for the output logic apply here. I could have written this as state and just a bit mask. I could have defined wire A equals state 0, wire B equals to state 1, etc. and just replaced this with A or E or F or G, and it all would have worked out nicely. You can hopefully see that using one hot encoding, we end up with very simple logic. The next state logic is very simple. The output logic's very simple. In some cases, for some special finite state machines, maybe it's possible to get even simpler next state and output logic using some other means. But as a general principle, one hot encoding leads to very simple logic expressions. And why is that useful? Well, for two reasons. Firstly, the total number of logic elements used. So yes, with one hot encoding we need to use more flip-flops, but often that's more than balanced by the fact that we use a lot less lookup tables because the combinational logic for the next state and output logic is so simple. The other benefit, which we will appreciate even more a bit later in the course, is that if the next state logic is very simple, then it can be computed quickly. And intuitively, for the finite state machine, the fastest it can operate is determined by how fast or slow it is to compute the next state logic. Because the rising edge of the clock will clock our flip-flop that photographs next state and stores it in state. And then before the next rising edge, the new state has to make its way round through the next state logic and back to the input of the flip-flop. And if that takes a long time, our finite state machine can't run very quickly. If our next state logic can be computed very quickly, then our finite state machine can run quickly. So when you need to have a fast, efficient finite state machine, sometimes one-hot encoding is what you want to do. As an exercise, if you're keen, you can go to Quartus, you can code up this finite state machine in canonical form, you can then have a look at how many logic elements are being used, and you can have a look at Fmax to see the fastest it can run at. Then you can, in that implementation, you can simply change your local param to use one-hot encoding. You don't have to do this. Quartus will figure this out for itself. You just change the local param here, and if the rest of your code is correct, Quartus will deduce this for itself. And then when you're using one-hot encoding, you can look again and see how many logic elements are being used and what is Fmax. Now for this particular design, I'm not sure which is faster. We're just saying as a general rule, often, but not always, one-hot encoding gives you the most efficient design.